However, in reality, in VLSI, you will also see log-normal distributions, you will see Poisson distributions, and you will also see Weibull distributions or extreme value theory being applied to various parts of VLSI design. Okay, each of these distributions could be of interest to you depending on what project you are working on. Suppose you're working on leakage control, then I would say you have to be very well aware and you have to take care of things by using log normal distribution. Suppose you're talking about gate dielectric breakdown, then I would want you to work with Weibull distribution and extreme value theory. But as VLSI designers, if you want to do some research and do some good design work also, it is important that you are comfortable with some of these very few but very important distributions that are fairly evident and fairly commonly used in VLSI design. I heard a sir sometimes, so there was a question. Please ask.
Sir, so this CPK thing, sir, if that's 1.33, I can see, I'm like, if I calculate, there is around 30% of loss or 33% of loss during the worst case. So shouldn't that be CPK should be greater than 2 then?
Yeah, for SRAMs, you want to put CPK greater than 2. Yes, you can say that.
Okay, sir. Okay.
But you will see that to make such kind of a process control, the complexity and the cost of the process increases. Therefore, we will talk about repair also.
Okay, sir.
Okay. Yeah.
Sir, is this 6 sigma only for memory or everywhere in all the chips we use 6 sigma variation?
So you tell me.
I want everything to be 6 sigma, but it is difficult to design having this.
And it's not even required now, Aditya. Suppose someone tells me that there are 500,000 flip-flops on a particular die. I know 5 sigma would suffice. Why do I go to 6 sigma?
So we design on the quantity, like how big is it?
Yeah, but we have to realize that depending on how big the die is, depending on how big the design is, the number of times the cell is repeated would increase. And that is what should guide you to decide whether you want to go to 6 sigma or 5 sigma or 3 sigma is sufficient. Okay. So do not rectify it as a rule. It's not a rule. I have gone through all this pain of explaining the statistics to you so that tomorrow, if you come to some other thing, you are able to decide how many sigma to qualify there. Okay. Don't rectify it as a rule. Raghav?
So like in the with the CPK, we are modeling the lot basically. Say if I have the fast lot, so I will get a certain mean.
Again, please don't get fixated with just the lot. Even in slow lot, even in typical lot, do you think that lot just gets a silicon would come only on slow lot or typical lot? No. If I say this is the rhombus, this was TT, this is SF, this is FS, FF and SS. Do you think that only these 5-6 points would exist? No.
No, sir.
Entire range would happen. You saw, remember the ellipse that you're talking about that we saw in the DVD course also? This is an entire range in which something would happen. So lot mat karo. Zyada mat faso uske andar, FS or SS ke andar.
Okay. So actually the question is ki, then what exactly, like I mean able to see the impact that the CPK has a different what I see in CP, but when we would be modeling say Monte Carlo, then what does Monte Carlo has control over? Does it shift the mean also, or does it only considers the sigma variation?
It depends it changes from tool to tool, Raghav, and it also changes from fab to fab. Some fabs would say that, okay, I will model the entire, all the lots and everything, all the variations in one simulation itself. That is called as global variations. Okay. At another time, you may say that, okay, I would want to qualify all the lots. So I will run Monte Carlo on all the lots separately. So I will qualify all these regions by myself. So that depends on your design methodology. You could already bring in the lot variation and then say, I will only see the variations of CP. Or you would say that, okay, I want to see variations due to CP and CPK simultaneously, and you would do a global simulation. It depends on methodology that you want to use. for your verification and whether the models that have been given by the process teams, they support it or not. You can do both ways.
And so similarly, the definition of how much sigma should I qualify will change also depending upon this event when I choose the global or these kind of.
Yes, you can always modify that, but yeah, it has to come from a good understanding of probability and statistics. Don't just randomly say I will qualify 3 sigma only because I'm here. Look at how many samples are we talking about on chip, and what would be the marginal yield loss because you qualified only 3 sigma and not 6 sigma when you were under slow lot. Okay.
Okay, sir.
But you can do that, yes, as a designer. See, if you notice, my endeavor across DVD and even MDT is to turn you into good designers, circuit designers. So I'm telling you all these levers so that you know that there is this flexibility that you can use as a designer. Okay. But again, do not get fixated. I'm giving you the concepts. I'm giving you why something is done a particular way so that you do not accept anything as a thumb rule or as a rule, as a something which is written in stone. I'm not giving you any diktats. I'm just showing you the path. Then you travel the path whenever you need to. Okay.
Okay, sir. Thank you, sir.
So where all do we need to look at mismatch in SRAMs? We already talked about these things: stability, SNM, right margin, right time, read current. All of those places we look at mismatch. When those of you are working on sense amplifiers, we would want to look at the mismatch of or the distribution of offset. We would like to look at the distribution of output delay and so on. So mismatch is something that we will play with a lot when we are working on memory design. Even when you're working on analog circuit design, for example, ADCs, DACs, PLLs, anything, you have to take care of mismatch. But in SRAMs, there are some places which you definitely need to take care of it. Okay. So these are about circuit level analysis. All that we're talking about is SRAM cell or a sense amplifier. So these are small circuits. But a memory will be functional not only when these small circuits are functional, but also when you always have the right kind of architecture so that SAEN arrival is at the right time. You remember this diagram where we said that, okay, when the worline is selected, the bit cell will discharge and differential will appear at the sense amplifier nodes. You remember this? What we want to say is that this SAEN should arrive at a time so that the minimum offset requirement of the sense amplifier is always met. Hello? You remember this constraint that we had?
Yes, sir.
How would you meet this constraint? There would be a memory with 100 rows. There would be a memory with 500 rows. There would be another memory with just 42 columns, another memory with 112 or 128 or 1K columns. How will you ensure that whatever the memory size is, SAEN arrives at the right time and not earlier or not later? So what happens when SAEN arrives later than the desired time? Sorry?
Sir, if SAN would arrive later, then maybe the clock goes low and the word line clock goes, and we do not, because basically everything would become high Z or something unknown state, internal nodes. If it
So, yeah, see, SAEN arrives along with reset. So when SAEN comes, at the same time, you start to reset the word lines, you start to recharge, recharge the bit lines and so on. So if SAEN arrives late, it means the reset of the memory has been delayed. It means the overall cycle time of the memory goes for a toss. If SAEN arrives early, what happens? And in that case, there is not the required mismatch, and there's not the required differential voltage at the sense amplifier inputs. And due to mismatch, your read operation can fail. So you do not want SAEN to arrive at very distant time from the optimal time. Are you able to see this? Hello?
Yes, sir.
So what you want is that when it is a large cut, let SAN arrive late. When it is a small instance, let SAN arrive fast enough. So to do this, what is done is that in the memory, we add what is called as a replica path. This replica path, what it does is it tracks the worst RCs for both word line and bit line, and then generates enable signal there. Okay.
So sir, that means the cycle time is controlled by the worst case bit cell here.
Not exactly the worst case bit cell, the worst placed bit cell.
Please, that's what I meant. Yeah, okay, the corner one.
Yeah, not the worst case. The worst case cell could be placed anywhere in the memory. The worst case cell could be here.
Yeah, sorry.
I don't know. But
Sorry.
the worst placed cell,
Got it.
the most distant placed cell. So yes, you're absolutely right in that, because I want that whatever cell is here, if this was also the worst cell, even then my memory should work. So I at least bring my replica paths, my word line and bit line RC should match. Okay. And then notice that I select more than one cell over here. Why do I need to select more than one cell over here? So those of you who were in the office hours yesterday, they should be able to answer right away. Raghav, you have a question? Your hand is raised. Okay.
We have to get the digital requirement to enable sense amplifier.
Yeah. See, the important thing is you cannot really have a sense amplifier on the replica bit line. If you make a real sense amplifier here also, then where will you bring its trigger from? You're stuck in the same loop. So what we say is we will put a inverter kind of sensor or something else, something which does not require an enable signal for itself. We will put something which would convert, which would sense that my replica bit line, let us call it as rep BL, has discharged, and now I can trigger sense amplifier on. If my replica BL has discharged enough, I would say that my actual bit line has also discharged. Let us say I want to discharge my actual bit line by 100 millivolts. And let us say the inverter over here trips at 300 millivolts. And I'm operating at 1 volts. How many cells should I put here?
Seven? No, so three only.
No. It trips at 300 millivolts, not 700 millivolts, not 300 millivolts below VDD. It trips when replica bit line has gone to 300 millivolts.
Oh, then 7.
Are you able to see it, everyone? I need to discharge replica bit line by 700 millivolts so that when SAN goes, it intercepts this particular bit cell or any bit cell at greater than 100 millivolts. To be able to do this, because they're the same cells that I have put in the replica column, I need to put at least 7 cells in the replica column, which would discharge. In a real array, only 1 row gets selected. Over here, I say that 7 rows should get selected.
Sorry, sir, I could not get. Can you repeat?
What did you not get?
Sir, 7 cell selecting, sir.
So the discharge rate of this cell and this cell is same. They are replica cells, same cells have been put at both the places.
Sir.
Now you want the actual bit lines to create a differential of 100 millivolts. But you want the replica bit line to have a differential of 700 millivolts. In the same time, how many cells on the replica bit line should discharge?
7 cells.
Is it okay?
Sir,
Huh? Talha, is it okay now?
Sir, no, sir.
No, not yet.
No, sir. Why is 700 millivolt there?
Because that is how I tuned the sense amplifier of the replica bit line. That is when I will trigger the SAEN.
Okay.
Let us say I tuned it at 600 millivolts. Then how many cells would I need?
Okay. I have tuned it. Okay. Now good.
Then you will need 6 cells.
Okay.
Hai na?
Yes.
So it is how I tuned this cell, this inverter there.
Okay.
Okay. So depending on how you tune the inverter, you will need to change the number of cells you require.
Okay, sir.
So this path, the number of cells which are selected by the replica word line over here, that should be programmable. I should be able to change the number of cells by just removing a little bit of metal one or something like that. Okay. So those projects which design the replica bit line or replica path, we talked about it in yesterday's office hours also. You have to take care of that. The cells are programmable. The word line is programmable, and whether it goes to VDD or ground, that should also be programmable.
sir,
Okay. Yes.
sir, how will you replicate this bit cell, sir, exactly? I mean, I didn't understand how are you doing that? I mean, keeping the same type
I
of.
just repeat the cell.
Okay, so sir, just repeating the cell means, okay, I do understand layout wise, I do understand that we can place the same layout over there. But this cell which we have should be the worst case, right? And we'll be replicating the same cell all over my memory cell, right? So how does that make a difference actually?
It doesn't. Replica bit cell is supposed to look exactly like the real bit cell.
Yes, sir, but I mean, the bit cell which we use should be the worst case, right? Worst case bit cell in
You have to
replica.
qualify the worst case bit cell. Be careful. You have to qualify the worst case bit cell, but in the replica bit line, many cells would be there and they will be selected in parallel. So you cannot really have the worst case cell there. You just put a replica cell.
Okay, so
Okay.
okay, sir. Yeah.
So what to take care of the worst case cell, what you may do is you may want to tune the inverter at the replica bit line at a still lower voltage, so that you need to discharge still more.
Sir, regarding this, I have a question, sir. What are the conditions for tuning this inverter? Means?
What are the conditions for tuning this inverter?
Yeah, means how you decided 700 millivolts.
Okay. I decided 700 millivolts because I wanted to keep more delay, let us say. Okay. I wanted to have bit line capacitance to play some role in determining my timing. If I had kept this thing at, let us say, the trip point at, let us say, 0.7, so only 300 millivolt discharge was required. So the bit line capacitance would have a lower role to play in determining how much delay is added. Are you able to see this?
Okay.
So it is about what kind of impact I expect because of bit line capacitance versus word line capacitance. Okay. Raghav, you have your hand raised.
Yes, sir. So I mean, I had a question. See, when we are thinking how many replica cells I should put in a replica bit line, then I'm only considering the discharge, right? Discharge time ki 100 millivolts. So, but for example, like once I get off the inverter, the sense enabled signal, when it will reach, that will also depend on the sense amplifier is of the leftmost cell or the rightmost cell. So that delay is also coming picture.
Yeah. So you have to consider everything. I'm just giving you a very simplistic view here. If I give you the complex view right here, तो आप लोग अपने बाल नोचना शुरू कर देंगे. That's why I'm giving you a very simplistic view. Even this is complex for you, is it not?
Yes, sir.
So that is why.
So, but that is also taken care by the programmable bit cells only, the replica bits. Okay.
Yes. You just, if you want more delays, you reduce the number of cells which would discharge. Automatically, it will take longer to discharge. If you want to you want SAN to write faster, you just increase the number of cells. Automatically, the discharge would be faster.
Yes, sir. Yes.
Okay. So, what does this mean? You remember this timing diagram? Remember we talked about replica word line then also? तब आपको समझ में नहीं आया होगा. But now I am formally introducing it to you. When the replica word line comes, after some time reset comes. And that is what then resets the memory and makes it available for next cycle. So you cannot really have a reset come far away. Okay. And just like for the read cycle, you have a replica write bit line and a write detect circuit also there, which generates the reset. So difference is in read cycle, the replica bit line discharge would directly generate the reset, whereas in a write cycle, there is an additional signal which is called as write detect. You want to ensure that the write operation has completed inside the memory cell, which would generate the reset. Okay. And then once the reset comes, then the same behavior is followed, but there is an additional observation that you have to make before you reset the memory in write cycle. Okay. Any questions?
Sir, why do we need write detect? Because we can just run a simulation where we can identify what's the worst placed bit cell, how much time it takes to write, and then after that automatically.
Yeah.
Right.
So what happens if it is a fast slot? Do you want to leave that kind of delay even in a fast slot?
No. Okay. Right. Got it.
You want to track something. That's why write detect also. Anything else?
But sir, when we are detecting write detect, that can cause stability issues because if you're reading it, because you're reading it, right?
So write detect would come from the right replica bit line.
Okay.
Not really worried about stability then.
Okay.